Hi everybody, welcome to Mount Philo State Park, and thank you so much for taking the time to make the trip out here, and thanks to Karina for being brave enough to lead the trip. So the theme of the lab today is to answer a pretty simple question. Why is there a mountain here at Mount Philo? If you look around you in the Champlain Valley, if you look off to your west in particular, you'll see the broad valley opening up. You might even catch a glimpse of Lake Champlain and the Adirondacks behind it. So overall, the Champlain Valley is pretty flat. A lot of the topography has been worn down. So why is there a mountain here that became a state park so people could see the view? What is the geologic sequence of events that led to this mountain? And so that's the overarching question today. And to answer this question, we're going to act a little bit like geologists. We're going to hike to the top of the mountain and stop at 6 sites along the way and make key observations at each site, and then we'll put those together into a story or a timeline of how Mount Philo came to be. And so that's a good point to mention. There will be a short lab write-up due 1 week from today. In addition to answering some short questions, you'll also need to fill out the timeline that's towards the back of your handout, and you'll also need to draw a cross-section of Mount Philo to scale based on the contour map that you've been handed. So take careful observations at each stop because you'll need to bring it all together at the end. In addition to your handout, you also have a color map that is shown here in this video as well. This is a hillshade, a colored hillshade rendered from LiDAR data. LiDAR is a type of airborne laser altimetry where they fly a plane across and they pulse laser beams down onto the surface, and it generates a very high resolution topography, much more detailed than topographic maps. So as a result, we can see every detail of the bare earth of Mount Philo. And it's really this LiDAR map, and in particular, you'll want to look at the LiDAR map without contours. So if the one you're looking at has contours, flip it over and find the one without contours. This will be the map you use to guide you on our field trip today. And as a starting point, let's work together to locate stop number 1. And that's right here. If you look at this long linear road, that's the road we came in on, and you are now in the parking lot. You can just see faintly the outline of the parking lot here where I've labeled number 1. And this is actually also stop number 1. So what are we going to see here? The main thing to point out at stop number 1 is actually a Champlain Sea shoreline. And if you're watching the video, you can see the shoreline. The best example of it is actually right here. It runs along the front of the mountain range, and I'll highlight that in a second for you. But first, just a reminder, what is the Champlain Sea? Well, you might remember as the glaciers retreated northward at the end of the last glacial cycle, they briefly blocked the outlet to the Champlain Valley. That created a lake, a freshwater lake, known as Lake Vermont, with an elevation of around 550 feet. After about 1,000 years of Lake Vermont, that ice retreated, and it opened up the northern end of the Champlain Basin. And at that time, the land was depressed and was below sea level. So ocean water actually rushed in and filled the Champlain Valley. And Mount Philo is a great place to think about that. As you look to your west, look at the topography below you. It's a big bathtub. Adirondacks on one side, Green Mountains on the other. This was all filled with an inland sea, including whales and seals, the fossils of which have actually been found right here in Charlotte. So here's a visual example of that. The light green is the extent of the Champlain Sea filling the valley, and the blue is the modern Lake Champlain. And here is the Champlain Sea shoreline traced for you. So right now in the parking lot, you're actually on a lower shoreline that was formed as the sea started to shrink. The highest Champlain Sea shoreline is traced in red. And actually, as you start up the road towards the top of Mount Philo, after about 2 minutes, look into the woods on your left or right, and you're going to see a flat area in the woods on your left and right. Looks like a bench or a topographic platform. That's going to be the Champlain Sea shoreline. So without further ado, let's get started. You're going to walk south out of the gravel parking lot and then turn left and follow the paved road all the way up to stop number 2. And Karina will let you know when you've arrived there. Okay, welcome to stop number 2. You've just come around a sharp hairpin turn. Looking both downhill and uphill, you can now see a lot of large, very angular quartzite boulders. This is the Moncton quartzite, and it is about 520 million years old. It's from the Cambrian period. It's formed in a shallow ocean, kind of like a tidal flat environment, very sandy. And the things to notice about this rockfall deposit are, how do we know it's a rockfall? Well, for one thing, notice all the rocks are the same lithology. Look around. They all have the same reddish color, the same bedding, some white beds in them. So they're all the same rock type, and they're all quite angular. They're not rounded. And so that tells us that they haven't been transported very far, right? If something is angular still, it means it hasn't been transported. So those two observations, similar lithology or similar rock type, plus the angularity of the boulders, suggest they are not glacial erratics, as you might have guessed. In fact, it's rockfall that fell down from this cliff near stop number 6 and tumbled down the hill here to stop number 2. Okay, so without further ado, pause the video and we'll continue up the road about a quarter mile to stop 3. And you'll know you're at stop 3 when keep an eye out on your left as you walk uphill, and you'll eventually see a very subtle outcrop of rock, shattered rock on your left at stop number 3. Okay, welcome to stop number 3. Hopefully you've found the one little place where you can actually see an outcrop of absolutely shattered shale. So how do we know this is an outcrop of shale? In fact, you can barely even tell it's rock. It's so shattered. Notice how platey it is, okay? Notice that the outcrop is falling apart, disaggregating. Take a minute and grab a piece of the shale, one of the pieces that's just sitting on the bank. Try to break it. Notice how easily it breaks. If you can see a fresh surface, notice how dark and fine-grained the rock is. These are all properties that help us identify this as shale. I'll pause the video while you take a quick look at it. Okay, so this isn't just any shale, this is the Eberville shale. And if you look at the front page of your handout, Figure 1 is a stratigraphic column. It shows the correct order, or the ideal order, in which the sedimentary rocks of the Champlain Valley are deposited. And if you look at the very top, you'll find the Eberville shale. If you look towards the bottom, you'll find the Moncton quartzite. So Moncton quartzite has a CM symbol, and the Eberville has an OI symbol up there at the very top. One interesting thing about the Eberville shale, it's actually one of the youngest rocks in the Champlain Valley. And it's actually a rock that was deposited just above the rocks that we saw at Crown Point last week. You might remember our last stop at Crown Point. I convinced you that you were looking at something that was turning more towards a shale. And I told you that above that, there was about 500 meters of additional shale. And this is that. The Eberville shale is that last shale deposited as the ocean basin was deepening in front of the encroaching Taconic Island arc. And there's nothing above the Eberville. This is the youngest rock. Okay, so let's pause the video and head further up the road about another quarter mile until there is an entrance to a gravel quarry on your left, and that will be stop 4. Okay, welcome to stop 4. Hopefully you're standing inside of a gravel quarry with debris pushed up on either side. If you haven't walked all the way in, make sure you've walked all the way into the gravel quarry. And look around you. Notice the walls. Notice this is an excavation. Look on your LiDAR image and notice it looks like a crater. So it's this really obvious thing where humans have excavated out a large amount of gravel. And actually, well, first I'll tell you the story. So essentially, this gravel pit is a deposit of coarse sand and gravel that is kind of moderately to poorly sorted, and it is interpreted to be a shoreline of Lake Vermont, where the waves of Lake Vermont were washing up against Mount Philo, working the sediment and moving it around and creating thick deposits of beach sediment. One reason we can infer this is because when you look at the sediment, you're going to see that it's pretty coarse. It does not have a silt or clay component. So we know that the environment the sediment was deposited was high energy, enough to remove the silt and clay component. Also, when you look at the gravel, you'll notice some of the pebbles are rounded, others are not, but at least a high proportion of this sediment has been worked by waves to the point that it's well rounded. Some of the sediment was probably derived more locally and didn't have a chance to be rounded. So before you move on, if you have time and you're doing well on time, look towards the southwest corner of the gravel pit, and you'll find a small pit exposure that I dug. At the base of that exposure, you can collect handfuls of fresh sand. Try to brush off the overburden and collect some fresh sand, and you can have a look at it for yourself and verify that indeed the substrate here is sand and gravel, and it is fairly well rounded. So one of the really cool things about this is, of course, if this was the high shoreline, that means that the summit of Mount Philo actually was a little island just barely poking out of Lake Vermont. So after you had a chance to look at the sediment, pause this, head about another quarter mile up the steep hill to stop 5 on your left, which will be right as you start to round the final hairpin. Okay, welcome to stop 5. This is a tough stop to find, but hopefully, if you look closely at about knee level, you'll see the final outcrop of shale. It will look very friable, very broken, right along almost at road level. And it should look very similar to the shale you saw at stop 3. So here you're able to see the shale rock in place. Okay, it hasn't been moved. It's actual in-place bedrock. But look at the hill slope above it. The shale disappears, and all we see are quartzite floating down from above. And I can tell you from experience that this is the highest level you can see the shale. From here, you pass directly into the Moncton quartzite. So at this point, I urge you to make sure you can see that, see the shale, see the quartzite above it, and then look back at your stratigraphic column, figure 1. And we need to figure out the answer to 2 questions. Why is the shale in direct contact with the Moncton quartzite? Does it make sense for them to be directly next to each other based on what you see in the stratigraphic column? And the second is, why is the quartzite overlying the shale here when the stratigraphic column shows that it should be below? Give those 2 questions some thought, talk it over with Karina, and then pause the video. And to get to stop 6, you're going to go all the way up the road onto the parking lot, walk through the parking lot, and continue. Keep going past a kind of lean-to building on your right. Keep going until you come into a clearing, and then walk up the quartzite to the main lookout, where you're looking now to the south and west. Welcome to stop 6. I'm going to quickly go through the last of these questions, and then I'll do a recap of what we've learned, and I hope you have a few extra minutes to enjoy looking out at the view before you have to hustle back to the bus. So, question 6.2, you are standing on the Moncton quartzite. Notice its characteristic reddish color. Question 6.3, how hard is this rock? You don't need to scratch it. I'll tell you, it's number 7 on the Mohs hardness scale, and it cannot be scratched even with steel. It will actually powder a Swiss Army knife. That's how hard quartzite is. It's made of pure fused quartz. It is one of the hardest rocks known to man. And do you think it would weather away faster or slower than the underlying shale? I'll let you think about that one. I'm going to jump to question 6.5. If you're at the viewpoint and you're looking over the metal railing towards the lake, turn around behind you. You'll see a bunch of bedding planes where you see flat surfaces of the quartzite dipping roughly 20 or 25 degrees off to the northeast. Those are the bedding planes of the Moncton quartzite. And one of the important observations here is that those bedding planes match almost exactly the slope of the backside of Mount Philo. And we'll come back to that in a second. So now I suggest you pause the video and look to the south and sketch Buck Mountain and Snake Mountain. As you look straight south, Snake Mountain will be the largest mountain, slightly to the right of the others, and Buck Mountain will be the one that looks similar in shape, but is the next one closer with a very steep front. So for question 6.4, please make a quick sketch of those. Doesn't have to be great, just a simple sketch, with a special attention to the fact that both Buck and Snake Mountain have relatively gentle slopes on their east side and relatively steep faces on their west side. And that is very similar to what Mount Philo has. Gentle on the east or northeast and steep on the west. So pause the video, finish your sketch, and then resume the video when you're ready for the final explanation. Great job, everybody. I hope that this has gone okay for you. So here is a figure that can help us bring it all together. This is the northeast to the southwest. Here you are standing on top of Mount Philo at stop number 6. And what we have here, what you have learned, is there's a fault separating the quartzite and placing the quartzite over the shale. Okay, you saw that at stop 5. You've seen these quartzite beds dipping about 25 degrees to the northwest, and we can infer that those quartzite beds match the dip of the fault because they were ramped up and over along the fault. So we can infer that those beds tell us what the fault geometry is down below. And one of the important ideas here is that the reason Mount Philo is still a mountain is that this sheet of quartzite has acted to protect it from glacial erosion over the eons. The quartzite was thrust up and over, and the quartzite is so hard that the glaciers have not been able to remove it. In fact, if you look just down below you where you walked up on the quartzite, you'll see lots of glacial striations, glacial polishing, and evidence that the glaciers really were scraping at the quartzite but couldn't remove it. So that's a key idea. We've got this cap of quartzite, and guess what? Both Buck Mountain and Snake Mountain also have a cap of quartzite sitting over shale, placed there by the Champlain thrust. So we have the exact same geology at those mountains as well. And so why do we have a steep frontal face, a steep west face? Well, the answer to that comes in part because of this shale. It's likely quite easy for the glaciers to erode this shale and undermine the west face of Mount Philo. And as that happens, this quartzite cliff is created and primed for rockfall, like the rocks that you saw at stop number 2. So it's really the glaciers eating away at this shale underneath that's allowed the mountain to maintain a steep western face and this kind of stark asymmetry. I think that's it for now. Hope you enjoyed this field trip, and let me know if you have any questions about the write-up. From here, you will do not go back the way you came. If you're looking out over the metal railing, you will now proceed to your right into the woods, and you'll find the main hiking trail that will lead you back to the buses. It will descend steeply at first, and then you'll come to a paved road. When you get to the paved road, you need to actually turn right and go uphill slightly, and then the trail will continue on the other side of the paved road, and you'll follow the trail all the way back to the parking lot. So you won't follow the paved road at all. You'll just cross it once to get back to the parking lot. Thanks for coming, everybody. Thank you so much for your time to take this longer field trip. Have a great day.